Have you ever really stopped to think about what happens after it rains? The water just seems to vanish into the ground. It looks simple, right? But it turns out there's a whole complex and honestly pretty dramatic story unfolding just beneath our feet. Today, we're going to dig into that hidden journey of water through soil, and it's a process that doesn't just shape our farms. It has these huge, unintended consequences that create massive dead zones in the ocean. So, let's get into it.
Right? It's a simple question we've all wondered about. You see the puddles disappear, the ground dries up, but where did that water actually go? Well, it's not just a straight shot down. It's more like a slow, intricate dance, and the soil itself is calling all the shots.
Okay, so once that water soaks in, its entire journey really boils down to two key processes. First, how it spreads out, and second, how it eventually leaves. And if you can get your head around these two stages, you've cracked the code to this whole story.
So, the first process is called redistribution. The best way to think about it is this. After the rain stops, the water doesn't just stop moving. Oh no, it keeps spreading out, moving sideways and downwards from the really wet soil near the surface to the drier soil deeper down. The soil is basically just trying to find its balance again.
And then there's the second process, drainage. This is the water that just keeps on going. It moves so deep that it gets way beyond the reach of any plant roots. This is the water that eventually recharges our groundwater. And as we're about to see how fast this happens, well, that changes everything.
All right, first up, let's take a closer look at that slow shuffle, how water moves through the soil. It's driven by some surprisingly complicated physics, but it's really cool.
This chart right here shows that redistribution in action. Take a look at those curves. They show the water content at different depths in clay soil. So just 5 minutes after the rain stops, that top curve shows the top 10 centimeters are totally saturated. But watch what happens over the next 24 hours. The surface starts to dry out as that water slowly pushes deeper, wetting the soil further down. It's like watching a slow-motion wave move right through the earth.
Now, you might have noticed on that graph that the biggest changes happen right at the beginning. The whole process slows down a lot over time. So why is that? Well, it turns out the soil has a few tricks up its sleeve to hang on to its water.
There are basically three big reasons for this slowdown. First, that initial push from the wet areas to the dry areas gets weaker as the water spreads out, kind of like a crowded room emptying out. At first, there's a big rush, but then it slows to a trickle. Second, as the soil dries, the little pathways for water actually shrink, making it harder for water to get through. And third, and this is a really fascinating one, is a property called hysteresis. It just means that soil holds onto water more tightly when it's drying than when it's getting wet. It's almost like it's reluctant to let that last little bit of water go.
Okay, so that's redistribution. Now let's talk about the second part of our story, drainage. This is where water doesn't just spread out, it actually leaves the root zone completely. And as you're about to see, the type of soil you have is a total game changer.
Not all soils are created equal, especially when it comes to drainage. Fine textured soils, like a loam or a clay, they have these tiny little pores, which makes it really hard for water to move through. So they drain super slowly. But on the other hand, you have coarse, sandy soils. They've got large pores that are like super highways for water, letting it drain incredibly fast.
And wow, this slide just makes that difference so clear. Over on the left, you've got loam soil. See how the lines, which show water content over 10 days, are all packed together? After a whole day, hardly any water has drained. Now, look at the sand on the right. It is a completely different story. In just that first day, the water content totally plummets. That soil is almost completely drained in just a fraction of the time. The texture of the soil is just a massive factor.
This whole idea of drainage just getting slower and slower, it actually challenges a long-held concept in soil science called field capacity. That was this idea that there's a certain point where drainage just stops. But as these graphs show us, and other research confirms, it doesn't really stop. It just gets incredibly, incredibly slow. The key thing to remember is this. In nature, there is no magic off switch for drainage.
But what if nature's slow, gradual drainage process just isn't good enough? Well, for centuries now, humans have been actively hacking the soil to try and bend its natural tendencies to our will.
I mean, if you're a farmer, especially one working with those fine-textured clay soils, slow drainage is a huge problem. You get waterlogged fields, which means plant roots can't get any oxygen, and that stunts their growth or even kills the entire crop. So if nature isn't going to drain the water fast enough, well, farmers have to take matters into their own hands.
And this is how they do it.
The modern solution is called tile drainage. Now, despite the name, they don't use tiles anymore. Instead, you've got these massive tractors with special plows, and they bury miles and miles of this corrugated, perforated plastic tubing deep underground. These tubes basically act like an artificial river system, collecting all that excess water and just whisking it away from the field.
And you know what? The results are absolutely dramatic. The benefits for farming are undeniable. By getting that extra water out of there, tile drains let oxygen get to the crop roots, which allows them to grow way deeper and stronger. And the result of that? Hugely increased productivity and much higher crop yields. It's turned land that was once just marginal into these incredibly fertile breadbaskets.
But, and you probably knew there was a but coming, this incredibly effective agricultural hack, this complete re-engineering of the land, has come with a river of unintended consequences that stretch far, far beyond the farm field.
And the scale we're talking about is just immense. This map shows the percentage of cropland that's been artificially drained. Just look at the American Midwest, the Corn Belt. In a lot of those counties, over half of the land is drained. We have fundamentally replumbed an enormous part of the entire continent.
So here's the problem. Those super efficient drainage pipes, they don't just carry water. They've become a superhighway for everything else in the soil, and that includes nitrogen and phosphorus from fertilizers. The stuff that's essential for crops in the field becomes a powerful pollutant the second it hits the water.
And this is where that superhighway ends. All that nutrient-packed water from millions of acres of farmland gets funneled into the Mississippi River, and it all empties out into the Gulf of Mexico. And the result is what you're looking at right here, a massive area of oxygen-deprived water. It's known as a hypoxic zone, or to put it more bluntly, the dead zone.
In 2014, the year this map was made, the dead zone covered over 5,000 square miles. I mean, to put that into perspective, that's an area bigger than the entire state of Connecticut, where the water at the bottom has so little oxygen that fish and shrimp just can't survive.
So how does this happen? Well, it's a pretty devastating chain reaction. First, all those nutrients from the farmland flow into the Gulf. This causes these massive algae blooms to just explode near the surface. Then, when all that algae dies, it sinks to the bottom, where bacteria start to decompose it. But, and this is the critical part, that decomposition process uses up all the available oxygen in the deep water. It literally suffocates the marine life, and that's what creates the dead zone.
So that hidden journey of water through the soil, it leads us right here. We brilliantly hacked the soil to grow more food, but in the process, we accidentally created this profound environmental problem hundreds of miles away. And it leaves us with this really critical question for our future. Having re-engineered the land to feed ourselves, can we now find a way to re-engineer our methods to heal the water?